I realized section 2.3 was pretty lengthy. The good news is section 2.6 should go much faster. We're going to begin with a discussion of continuity. And the simplest way to understand that is that a function is continuous over an interval of its domain if its hand-drawn graph over that interval can be sketched without lifting the pencil from the paper. As long as it is possible to draw the entire thing without any holes, any stops or starts, no gaps, you have a function that is continuous. Now, as you look at these two graphs in classroom example 1, I want you to look closely at A, and what we are asked to do is to describe or define the intervals of continuity for this function. So the first question we have to decide is the entire function continuous? Do we see any holes, any gaps, anything that's missing? And if you zoom in, I am hoping you recognize there is an issue going on right there, because that open circle means there is a hole there. There's something that gets skipped over in the graph. Because of that, the entire function is not continuous. There are two different intervals of continuity. It would be continuous up to a certain point, and then you'd have to skip over the missing point, and then you would have continuity after that. So when we identify the interval of continuity, remember it goes with the domain, so you have to think in terms of x values. And if I pay attention to this graph, remember it's not that this arrow is pointing down, but it's the fact that if I consider this to be extended, it keeps going to the left. Because as I look at x values, I'm asking myself, what is the furthest value to the left? Well, that means this is going to start at negative infinity, and it is continuous all the way until we get to this point where the open circle is. Now, carefully decide, what do we need to close this interval with? I hope you recognize that it needs to be 0. Not 2. 2 is the y value at that point. Remember, we have to use the x value. So we have x's that are continuous from negative infinity to 0. Now, does 0 need a parentheses or a bracket? Well, again, I hope you recognize because of the open circle, that's why we have a parentheses. We're skipping over the point 0. Since there is another interval that is continuous, we need the union sign. And the second portion of continuity begins at 0 and goes to positive infinity. And again, because 0 has that open circle, make sure you use a parentheses around that interval as well. Now, as you look at graph B, that is a section of linear equations that have been joined together. There's not one particular graph that would form this. So again, we would call it a piecewise function. But if I look at where these pieces are put together, I don't see any gaps or any holes. So would it be continuous over the entire domain? This one is. And that would mean, because of the extension of the arrows and the fact that it continues forever to the left and it will continue forever to the right, this is continuous from negative infinity to positive infinity. So very similar to when we gave intervals that were increasing, decreasing, and constant, when we're giving intervals of continuity, we also will have to make sure we're only using x values, because we're answering the interval question using the domain values, using the x values. Also, when we're talking about increasing, decreasing, and constant, we have to be very, very careful about how the symbols are written, whether we have open circles or closed circles. It won't be a function if we have any points that are overlapping. If we're just talking about continuity, it may or may not be a function. Now, if we are looking at these different graphs that we're about to see. These will all be functions, and I want you to be able to identify them by sight. So many of these will be familiar. We're going to go through this very quickly, and truthfully, this just becomes something for you to study, and then you will answer some questions where you may have to match a particular graph to a certain equation or some other feature. You may have to identify some other characteristic of it. So you're going to want to be able to identify what we would have called parent functions. If you had learned this in Algebra 2 in high school, we're going to have some basic functions that I want you to recognize. The first is called the identity function. Notice that it's f of x equals x. That would be the same as y equals x, which means we're talking about the basic linear function. And there's the graph that goes with it. You should already remember, if it's linear, the domain will be negative infinity to positive infinity, as will the range. We do not have any x values or y values that would be excluded from these graphs when they're linear. Notice also, for the basic parent, if it's y equals x, that the function will be increasing on its entire domain. That's true. And it will be continuous on its entire domain. There will not be any stops, starts, anything out of any gaps that would exist. Okay, it is time to go to the squaring function, or y equals x squared, which happens to be a quadratic equation. So we're going to talk about quadratic functions. We know this would be the graph for the basic parent, y equals x squared. Now, if it's quadratic, we know it's a function. We should also remember the domain will be negative infinity to positive infinity. There's not any value of x we cannot put into that equation and square. We can square any number we want. However, if I look at this graph and I think about the equation, my range is going to be restricted from 0 to positive infinity. That's because when I square any number, I'm going to get back a positive number unless the number was 0, and that makes 0 the smallest value I can get back. So a parenthesis goes around infinity, but we would want to bracket around 0 because 0 could be included in this domain. It is included in this particular graph. Now, this one has a section or an interval that decreases and one that increases. If I pay attention to this graph, moving from left to right, the section that will be decreasing starts from negative infinity and it decreases until 0. Now, as far as when you have a graph and there aren't open and closed circles, it just is continuous over the whole interval, you get to determine whether you want to include, in this case, the point 0 as either being on the section that decreases or the section that increases. And your computerized homework, the way that it's graded, is very flexible on this. So you can choose whether you want it to be a parenthesis or a bracket. You can make the argument that at one particular point it's doing neither of the two. It's not increasing or decreasing, so it's up to you. Now, the interval that would be increasing starts at 0 and goes to positive infinity. That would be the section of the graph. As I move from left to right, it goes up. And it is continuous on the entire domain. There is no gaps, stops, or starts. Now, the cubic function, y equals x cubed, looks like this. I would describe it as something of an S curve where the ends are stretched out vertically. Notice that it extends up in the first quadrant and it extends down in the third quadrant. Okay? You want to get this image in your head. It passes through the origin and then it's going to stretch out vertically in the first and the third quadrants. Now, if I ask you the question about domain, I realize it's going down so quickly here in the third quadrant that it almost looks like the line is vertical. But think about it for a minute. Is it still scooting over to the left? If I put in some value for x and I cube it, can I get two different values of y for the same x? No, it's not possible. It's just that it is going down so rapidly, it is so steep, it almost looks vertical. But it's not. It is still moving to the left. That means my domain is negative infinity to positive infinity. If this thing stretches out long enough, I can eventually get it wide enough to cover any x I want. Same thing with the range, although the range is definitely more obvious because of the fact that it's been stretched vertically. I can see that it is going down in the third quadrant forever. It's going up in the first quadrant. So it will go from negative infinity to positive infinity on the range. That will always be true with these cubic functions. Now, it's increasing on the entire domain because as I look from left to right, it's always going up. There's not any place where it would be decreasing. It's increasing on the entire domain, and it is continuous on the entire domain. Time to go to the next page. The square root function, y equals the square root of x, looks like it is half of a sideways parabola. If you look at this graph, if I were to sketch this part in, what you would see would be the equation x equals y squared. Now the problem with that is that doesn't pass a vertical line test. That is not a function. We can have two different y's that would go to the same x if we did that. So in order for it to be a function, we would have to use the square root of x and only have half of that sideways parabola. If we actually wrote it as x equals y squared, it's not a function. So since we're dealing with functions, this is what it looks like. So you want to keep that in mind. It's half of a sideways parabola. It's in the first quadrant. Now my domain will not be all real numbers here. It's not negative infinity to positive infinity, because if I look at that x, what would be the possible numbers I can put under a square root sign? Well, if I'm working with real numbers, I can't use negatives. That means my domain goes from 0 to positive infinity, and I can use 0, so I use a bracket around 0. Now, as far as my range, those would be the y values I get back when I evaluate the square root of some number. And if it is an equation that's written with the square root already in place, that means it's a positive or a principal square root. I can't get back a negative value for the range either. So my range is also 0 to positive infinity with a bracket around the 0. Notice this is increasing on the entire domain, and it is continuous on the entire domain. Everything in the domain will still be increasing as you move to the right. Let's look at the cube root function. So just like we had a cubic, now we'll have a cube root, and if you look at this graph, you see an interesting thing. Instead of it being an S-curve that's been stretched vertically, it looks sort of like an S-curve that's been stretched horizontally. It's still contained in the first quadrant and the third quadrant. However, it is stretched out horizontally. Now, because of that, if I were to ask you about domain, I think it's pretty obvious. I can use any x value in the world, negative infinity to positive infinity. Even though there is a radical, it's a cube root. Since that index is an odd number, I can put negatives underneath. If I asked you what's the cubed root of -1, I'm asking you what can you multiply times itself 3 times, and the answer is -1. And the number that would do that is -1. -1 times -1 times -1 gives you -1. So if I took the cubed root of -1, I get -1. Now my range, just like on the cubic function where we had to stop and think, even though it looked like it was flattening out, it really isn't. This one is the same way. It almost looks like it's horizontal as you stretch out to the sides, but it's not. If I were to put in some value for x, I can't get two different y's. It may not be going up or down very quickly, but it is still moving up and down. So my range is also negative infinity to positive infinity. You want to get confident with these graphs and this information about it. If you look at this graph, it continues to increase as you move across the entire graph. So it increases on the entire domain, and it is continuous on the entire domain. Let's go to the next page. The absolute value function. We did look at an equation that had an absolute value in it before. The one we saw was not a function because it was x equals the absolute value of y. This is y equals the absolute value of x, and it is a function. If you were to look at this graph, you can see that it would pass a vertical line test. And if I ask myself about domain, those x's extend both directions. I could put any number I want in for x. So negative infinity to positive infinity is my domain. But I do have a restriction on my range. If I look at this graph, when I take the absolute value of a number, I can't get a negative. This will never go below 0. So my range goes from 0 to positive infinity. Now, again, I have a section that decreases and a section that increases, just as we saw with the quadratic. And on this one, it decreases from negative infinity to 0, and it increases from 0 to positive infinity, and it is continuous on the entire domain. The last thing we're going to talk about would be piecewise functions. We've already looked at them. We know when we have a graph and there are pieces of lines that are put together, it's a piecewise function. So as we look at this particular equation, what I will tell you is anything I ask you to do with piecewise functions, I will keep it restricted to things that are linear. I wouldn't expect you to graph part of a quadratic or something else and make it piecewise. But this part right here is called your domain restriction. Remember, if we don't restrict the domain, it wouldn't be a function because we can't have two equations that crisscross and wouldn't pass a vertical line test. So what we will do is graph these based on this domain restriction, and that means we're going to need to make that table. So I'm going to take the first function and I'm going to plug in x values to 2x plus 4, find some y values, so I'll have ordered pairs I can graph. But I pay attention to this domain restriction because it says my x's should be less than 1. Now, in order to graph this, I would say let's find out what the y value is when x is 1. Because if I'm going to be drawing a line and I want everything to the left of when x is 1, I need to know where that point is, and I'm going to put an open circle there to show don't count it, but start here. So if I were to plug in 1 for x, 2 times 1 is 2, 2 plus 4 is 6, that means the ordered pair 1, 6 is on the graph, and it will be an open circle. So if I go to 1, 6 and put an open circle, I will now find other points that, remember, if I'm drawing a line, I need 3 points to make sure I haven't made any mistakes, and then I can draw in the rest of this graph. All right, what value? Pick something that would be less than 1. I need 0, because remember, my values have to be less than 1. So if I were to plug in 0, 2 times 0 plus 4 means when x is 0, y will be 4. So I want to put that point on the graph. Well, if I can get it to mark, there we go. And I need one more value that's less than 1. Let's try negative 1. So if I plug in negative 1 for x, 2 times negative 1 is negative 2, and negative 2 plus 4 gives me a positive 2. So when x is negative 1, y is positive 2. I now have 3 points, and I can connect them, and that would be the top part of this piecewise function. I still have to come up with the points that I need to graph the bottom part of this piecewise function. So it's time to make another table. This time, I'm plugging into 4 minus x in order to find my ordered pairs. And according to my domain restriction, my x's should be greater than or equal to 1. So I want to start with an x value of 1. And when I plug that in and simplify, when x is 1, y would be 3. Now, because of the or equal to, this needs to be a closed circle. It's included in the graph. So at 1, 3, I have a closed circle. Since x's are supposed to be greater than or equal to 1 is my domain restriction, I'm going to choose 2. And when I plug that in, 4 minus 2 is 2. So when x is 2, y is 2. So that point right there. And let's see what happens if we use 4. 4 minus 4, well, when x is 4, y is 0. Now, you may have selected other values. As long as they fit within the domain restriction, that's perfectly okay. Our graph should still end up looking the same. So when we connect these points, this should be an idea of what your graph will look like. Now, if I give you the domain restriction but no graph, I might ask you to do something like this as well. So let's say with the domain restriction that was up there, suppose I had asked you to find f of negative 10. Well, even if I'm looking at this graph, I don't see what that is. But that means when I go back to this domain restriction, I had two equations. I have to choose the correct one to plug into. Which one does negative 10 fit the domain restriction? Is it the top equation or the bottom? Well, you better recognize that it goes into the top equation. That's what I use for x values that are less than 1. So I'm going to plug negative 10 into 2x plus 4. And I do not plug it into both. If you give me two answers on a question like this, you will have it wrong. You only plug into the one equation that fits the domain restriction. So 2 times negative 10 plus 4 means I have 2 times negative 10 is negative 20, and negative 20 plus 4 would give you negative 16. So f of negative 10 would be negative 16. Likewise, I might ask you to do something like evaluate f of 12. Now, if I gave you that and you go back and look at the domain restriction, hopefully you're going to recognize that means I need to plug into the bottom equation, because that's what I use for x's that are greater than or equal to 1. So if I plug that into 4 minus x, 4 minus 12 will equal negative 8. So be prepared to answer questions either direction with that. And it's time to go to the last page. We're going to make a modification here because I did tell you I would not give you anything that is quadratic. So this bottom equation, which is written with something that's quadratic, change that to a 3. I want you to see what happens if you have to graph a constant equation. There's no variable there. It's just f of x equals 3. So let's go through the same process that we used a moment ago. We're going to have to make a table. We're going to plug into negative x minus 2 in order to get ordered pairs for this top equation. Look at your domain restriction. We're supposed to use it when x is less than or equal to 0. So our starting point will be 0 because we need to know what happens when x is 0. And if I plug in and simplify, I should have the ordered pair 0, negative 2. Now, look at your inequality. Does it need to be an open circle or a closed circle? Well, because of the or equal to, this is a closed circle. So I'm going to go to 0, -2, and put my closed circle on there. All right, let's pick something else that is less than 0. Maybe something like -2. So if I were to copy this down, put a parenthesis where my x was, and now plug the -2 inside, notice what happens. I have a -2. That turns into +2 minus 2, which is 0. I'm going to have the point -2, 0 on my graph. So I plot that. Let's try -3. And if I were to plug in -3 for x and clean up, I have 3 minus 2, which is 1. I'm going to have -3, 1, which is this point right here. And now I can draw the line, and I have half of my graph done. For the bottom equation, since f of x equals 3 when x is greater than 0, you may know how to go straight to the graph to put it on, but if you don't, this is a very simple way to do it. In order to get your ordered pair, I just need to make sure I stay with my domain restriction. X's are supposed to be greater than 0, so that means I need to start by using 0. But notice there's no place to plug in the x. It already tells me that y is 3. So at the ordered pair 0, 3, I just look at the inequality and ask, is it open or closed? Since there's no or equal to, I need an open circle at 0, 3. So I'm going to put that on my graph. Ooh, I kind of missed on that. Sorry. It should be at 0, 3. Let me scoot it over just a little bit. Ooh, that's even worse. Sorry. Let's go for another x greater than 0. Let's say x is 2. That means I have 2, 3. And let's go with maybe 4. And that would mean I'd also have the ordered pair 4, 3. So I come over here. The one thing that is constant is that my y value is 3. Oh my. Sorry about that. I was very sloppy on trying to make those points. But I know I have a horizontal line at y equals 3 with an open circle at the point 0, 3. And that's how I would graph it. And then again, you could be asked to identify things such as what would be f of 19. Well, you have to decide, am I plugging into the top equation or the bottom? Looking at my domain restriction, I plug in at the bottom. That means it would be equal to 3. If I asked you what is f of -1, then when I look at the domain restriction, -1 is less than 0, so I plug into the top equation. So I would have -1 minus 2. 1 minus 2 is -1.